Okay, during the Wednesday 31st, we had a breakout room. A few people participated. I decided to go over some of the problems, put the solution in, and they would be useful for the test. The test is coming up. So what we have here, number of problems from the textbook, different alkene, as you can see, and these alkenes, some with the structure, some with name, and the reagents were given to us, and we're asked what the product is. In some cases, we don't have the product. So we need to follow the reagents and set up the reagents and see what they do and what they provide for us. So I'm going to go jump. There are like 2 pages, and I'm going to jump directly to the homework assignment. Sorry, 3 pages, and go from there. So what we have, first problem is some of them are going more details for you, so we know exactly how to approach this kind of problem. So we have again a alkene here. The alkene has an stereocenter. The product shows as a alkene halide as a stereocenter, but plus we have to pay attention. It says plus enantiomers. So that means the product is really a mixture of the two, and it's not alone. So the other product that is not shown is a methyl group going away from us and the Br coming toward us. So quickly we learn that if we have a 50-50% of RNS mixture, that means we had a carbocation intermediate. So definitely we had a carbocation. As soon as we learned that there was a carbocation, so we really need to think about a carbocation as always or most of the time is associated with a rearrangement. And it's the case here. We can see a double bond that we had here. So if you look at this double bond here and look at the carbon that we have here, we can see the substitution, which is for the Br, is in a different location. So if this was carbon number 1, carbon number 2, carbon number 3, then the Br from HBr has gone to carbon number 3. So it really has rearranged. So we know that an alkene is basically a base. We know that HBr is an acid. So the combination of the two basically generate a carbocation. Let's go look at it. So if I look at the starting material that we have here, and then we have the stereocenter here, and then we have the HBr. Remember, we want to introduce a carbocation. That this carbocation is going to be more a stable one. So hopefully we get the secondary carbocation first. So if I move the pi bond from here as a base, and this is my acid, and bond breaks down, so I would make a first carbocation, which is a secondary carbocation, and this carbon that had 2 H's, now just for this time drawing it, so we had 2 H's to begin with, so we add the third H, so there's no charge on that. So we have a secondary carbocation, but this secondary carbocation can rearrange. Remember that there's a little H here we didn't show. If this proton and electron, so it's a H now, hydrogen moves with the 1-2 shift here, so I can change the carbocation to a tertiary carbocation. So we have now a tertiary carbocation, and the methyl group is still there. Now, what happens now? We went from a sp3 orbital to an sp2 orbital, and the sp2 orbital is a flat structure. sp2 orbital. So sp2 orbital is a flat structure. So sp2 orbital is a flat structure. Now we have an electrophile here. So we have an electrophile. The nucleophile is basically the Br minus that we have from here. So the Br minus is the nucleophile. Now if this Br minus comes from the top or the bottom, the textbook shows coming from the bottom. So the Br minus comes from the bottom, pushes the methyl group toward us, and the product would be what has shown on the textbook, that methyl group coming toward us, and the Br is behind the scene or behind the paper. So Br would be here. Now, if the Br comes from the top, pushes the methyl group away from us, and the Br basically is coming toward us. So that's why it shows only here and call this one as enantiomer to save paper and drawing. So this was the first one. So we learned a few things from here. We look at the starting material. We look at the product. We pay attention that the product says it's the product plus enantiomers. So that means the carbocation was generated and the nucleophile attacks from the top and from the bottom to make both isomers. And we also notice that the stereochemistry here is gone and it disappears. Here's only one enantiomer. So that means there is a carbocation, and that carbocation has been rearranged because the double bond is over here, not here. So that was problem number 1. Let's go look at problem number 2. Problem number 2 is similar to the problem number 1. It's showing us that we have a stereocenter. The stereocenter in this case is completely gone. So you can see we start with the stereocenter here, and that stereocenter is not there anymore. It's not showing any bond coming toward us or going away from us. We still have a pi bond, which is a base. We have an acid. Again, most cases, a combination of acid and base in the pi bond system generate a carbocation. And that carbocation in this case has rearranged. So let's take a look at it. So we start with the pi bond as a base. We start as a pi bond as a base. So we have the base as HCl here. So the pi bond generates a secondary carbocation first. So we have a secondary carbocation. Stereocenter is still here, ethyl group. So we added H here. We're not going to show the H now. And the carbocation would be here. This is only one H here. So from now on, we're going to practice to show the carbocation without the H. So we have a carbocation and a Cl minus. So if you think about the Cl minus as a nucleophile and carbocation is electrophile, that is correct. So the reaction would go and make the starting material. That could happen. But let's say if we can make a better carbocation, and then remember there is a extra H here, so I'm going to draw the H. So we can see that we can do a 1,2 hydrate shift, we call that. And if that moves over here, so we generate a tertiary carbocation. Now that tertiary carbocation is an sp2, not sp3. So it's flat structure. It's a flat structure. So ethyl group basically now, or this carbon here, is going to lose its stereochemistry. It's not stereochemistry anymore. Because it's on 3 bonds and it's a carbocation. No stereochemistry. No stereochemistry. Now we have a better carbocation, which is a tertiary carbocation versus a secondary carbocation. So we're going to look at the electrophile that we can have here. Electrophile is Cl minus, comes back and react with the tertiary carbocation. So it comes back, react with the tertiary carbocation as a nucleophile, make a new bond with the electrophile. Again, remember carbocation is an electrophile. So the product that we're going to generate has the ethyl group and a new bond to the Cl. And that's what the product was shown at the beginning of the practice. So we generate a mechanism or explain the reason behind this. So let's look at the problem number 3. Problem number 3 is a little bit different. So number 3 is actually asking us to do a little bit different. We're asking us to go from a name to the product, and the product is not given to us. So what we need to draw is we need to draw the starting material. We have a 2-cyclohexyl, 4-methyl, 2-pentene. So the excuse me. So the pent is really the pent is the main part, the P, pentane, 5 carbon. So again, as I said before, to go from a English name to a chemical structure, start with the drawing the 5 carbon units. So let's draw 5 carbon units. So we have 1, 2, 3, 4, 5. So that's now numbering system. You can number from the left to right or right to left. I have a habit to write it from left to right, but it doesn't really make any difference. So I put 3, 4, and 5. Now I go back position 2. We have the double bond. We have position 2. We have a double bond, so we draw the position 2 double bond. It doesn't specify is that the E or Z, so I draw a E isomer. It doesn't really make a difference. Then at position 2, I put my 2 here, but there is a cyclohexyl. Got messy here, so I'm going to redraw it. Position 2, we have a cyclohexyl. So we have a cyclohexyl position 2. Then we have the 1, 2, 3. Position 4, we have a methyl group. We have a methyl group. I think that's it. And then position 5. Now what we're adding here, DCl. Wow, what is it, DCl? It's the same as HCl, right? So instead of the H as a proton, we have deuterium, which is the heavy part of the H. So it behaves the same thing. So if I draw a D and a Cl here, like I was drawing a H and a Cl. Remember, this is partially negative, partially positive. This is my acid, right? My acid. And this is my base. And I open it as such to make a better carbocation. I want to make a tertiary carbocation. So if I draw the arrow this way and this way, so what I'm making here is a carbocation, a tertiary carbocation. Again, my cyclohexane is a little bit ugly looking, but you realize it. So now I have a carbocation here. So I have a carbocation here, and the carbocation is basically now looking for looking for a nucleophile. The nucleophile is Cl minus here, and I forgot to draw the arrow here. So this Cl minus comes back, and when we adding the D here, when we have the D here, so I have to show the D here, right? D here, there was a H there, so we can show the H and D. Cl minus, again my minus is a little bit close to the D, so I'm going to draw a little circle around it. Now the Cl minus is going to go back to the electrophile. I'll try to make it a little bit better looking. So we have the 5-member ring, 1, 2, 3, 4, 5, the methyl group. Now I'm going to draw a little bit better. So I have the D here, the H here, then Cl here, and we had that cyclohexyl. So we didn't really do anything with the cyclohexyl, so it was there as a substitution. So this would be the final product. So here we go to the number 4. Again, we have the same thing. We have an alkene, we have a HCl, and we learned that basically this is an acid, this is a base. Reaction generates a carbocation. We have a stereocenter here. So let's see what we can learn from this reaction. Now, if you generate a carbocation here, so we're going to generate a carbocation. Now we have to decide if that carbocation is going to rearrange or not. Now that Cl, we're going to see that Cl is going to prevent from a carbocation rearrangement. So let's do that and generate a carbocation. Again, we have a H and a Cl. So draw the arrow or arrows. Again, you want to make a secondary carbocation, not a primary carbocation. So again, we decided not to show the H's, decided not to show the S's, and show only the carbocation. So the carbocation that I'm going to make would be here, plus a Cl minus here. Of course, Cl minus is not going back to the carbocation because it would make the same product. So now, what are we going to do with the carbocation? There is an H there, right? There's an H here. So let's look at the H here. So we have an H here. Would that move to the carbocation? Let's give it a try. Now, if I move this H with the electrons, which is 1,2 hydride shift here, the carbocation that I'm going to make has a Cl attached to it. So this is the carbocation. The sun is coming to window. I'll move the paper a little bit here. So this carbocation now has a Cl. Remember, the Cl is electronegative, so pulls electron away. Pulls electron away. That makes this carbocation with the Cl not very attractive. So it makes the carbocation even worse. If this was an electron donating group, it would have been okay. But it's electron withdrawing group, so it's not good. So we're going to tell ourselves that this carbocation really doesn't form. So we are basically stuck with the secondary carbocation. So we couldn't make that. So we're back to this. So I'll redraw it. So we have a carbocation here. So we did not undo anything with the Cl. So Cl is there, right? And it's going away from us. So now we have another Cl coming in, right? With the Cl. So the interesting is now, because we have a stereocenter here, if the Cl comes from the top, so that Cl and this Cl are anti to each other. And if it comes from the bottom, would be the same as this, so it would be syn addition. So we really make two new stereoisomers that they are distereomers. So let's take a look at it. So if it comes from the top, so let's draw it from the top. So we have the Cl here. So we put the Cl coming from the top, remember? Now, if the Cl comes from the bottom, so this is from the top, right? If the Cl comes from the bottom, so we have a Cl like this. So these two, they didn't put an R and S there, but these two diastereomers. So we can actually practice this in the laboratory, and we can see we make two diastereomers. Diastereomers usually have different melting point and boiling point, and the GT and the instruments are different. So we can differentiate the two easily, that they're the two products. So the two products from this reaction is this product and this product here, but they are diastereomers. So we did problem number 4.